Ladies and gents, welcome to this week's Geotalks Online. Thank you all for joining us. It's fantastic to see all of you joining us on Zoom, but also on YouTube. And this week we are experimenting and having the talks live as well. So in the room next door are a bunch of people enjoying beers. And Roger is going to be presenting from G101. So we've had a little bit of technical hiccups getting everything sorted. But I think we are ready to go right now. So thank you, Roger and Lou, for agreeing to give this talk. Smiling. And I can see Roger is trying to talk. So welcome, everyone. Thank you once again. Let me introduce the speakers before we go any further. So as you probably all know, Roger Gibson is an ad hominem professor of metamorphic petrology and structural geology at Wits University, and has been was head of school for many, many years. He completed his undergrad studies at the University of Natal and his PhD at Cambridge, and then joined the department here in 1990. Lou did his undergrad and postgrad work in the USA, and then was then a postdoc both at NASA and the Lunar and Planetary Institute in America, and thereafter joined RAU, which is now UJ, and then joined Wits in 2001. And he is a distinguished professor and an A-rated scientist in South Africa. So thank you both for agreeing to give this talk. And we really look forward to hearing about this interesting study on a recent meteorite discovery. So I'm going to stop my sharing now and hand over to Roger. It might just be a slight delay in getting things sorted, so just bear with us for a moment.
Okay, thanks, Grant. I think thanks, because I didn't hear a word you said, and you were smiling rather broadly when you introduced us. Can you hear? Right. Okay. Thanks. Good evening, everyone, and thank you for signing in. This is going to be part of a double act that we're going to have. I just need to call up my slides, which I presume means, Leo, we're in, are we? Okay. Okay. Sorry? But we're not, no, sorry, Grant, I'm not in the act of, oh, there it goes. Right. So I'm showing a video captured by a CCTV camera on the 2nd of June 2018 in Ottersdal near the
Not sharing.
Okay. Am I in sound?
We are on sound, but let's just show on the screen.
Okay, that helps. All these things you remember when you're sitting down. Go back. Can we reduce this?
Yeah, we will not.
So if you want me to stay in the frame, I'll need to see what I'm using.
Right, now you're good to go.
So where's me?
Look up when you start speaking.
And I'm all yeah. Right. Thanks, Grant, and sorry for that technical glitch. I'm about to show a video from a CCTV camera from a farm near Ottersdal in the Northwest Province from the 2nd of June 2018. And that event triggered a project that lasted about a year involving 66 scientists from 12 countries. And Lou and I were very fortunate to be part of that international team. And so we want to present our results as our contribution to the project, as well as the some of the general results from the project. So what we're going to do is I will talk briefly about our results and the search for what became known as the Motopi pan meteorite. And then Lou is going to take over and talk about some of the general geochemical, isotopic, and geochronological results that came out of the broader project, and how we can then tie this meteorite back to its origin in space and potentially its original source. So bolides or meteor fireballs are quite a roller coaster ride in geosciences, because you normally hear about them first from social media or from the news media, and you are relying on very brief spottings that are very, very chaotic. So this was my first alert to what happened on the 2nd of June in 2018, was the news report the next day showing the video that I've just shown, but some of the eyewitness reports that obviously confirmed there was a bolide, but actually said, among other things, that they thought there were two. And so this is one of the challenges, is that when you try and coordinate the eyewitness reports, everyone thinks this thing happened right next to them. So you end up with quite a chaotic turn of events. So I just want to briefly say what actually happened. So we received news of this the day after the event, and I immediately started to try and find out more. There wasn't much else in the local news and media. But on the Monday, I received a call from Dr. Thomas Kohut from the Finnish Fireball Network, who monitor these bolides coming into the upper atmosphere. And he indicated that they had well-constrained trajectory data and would like to talk to researchers in Southern Africa about possibly finding the meteorite. So I got in contact with colleagues in Botswana, and they started a whole bunch of things because of legislation and trying to find out where they could go. Between the Monday and about for the next 2 weeks or so, we were involved in a bunch of different techniques to try and constrain where the meteorite might have actually fallen. And by the 18th of June, permission had been given and money found to launch the first search party that actually ended up finding the first meteorite. It was only 3 search parties later that any other meteorites were found. And from those, we ended up at Wits with our first samples to look at. 5 of the samples were sent to us. And since then, one other big meteorite has been found, and the paper was finally published in Meteoritics and Planetary Sciences in April of this year. So there's the paper with its host of authors. So what actually happened? Can we move this at all, Grant? Okay. So in terms of the astronomical observations, on the morning of that Saturday, the Mount Lemmon telescope in Arizona, which is dedicated to finding near-Earth asteroids, spotted this asteroid, which was provisionally given this designation over here, and it was said to be possibly on an Earth-crossing orbit. The system was then bumped up to the Atlas survey system, which actually worked out there was going to be a definite impact, and it was going to happen somewhere in Southern Africa, possibly in Namibia. This information only came through, though, after the event itself. So what did the information actually indicate? Well, from Ottosdal, where that CCTV camera was, it points in a roughly northwesterly direction. And so what we were seeing was something that occurred on a line heading north-northwest from Ottosdal, which puts us in Botswana in a large area that's largely unpopulated in the Central Kalahari Game Reserve. That was good news and bad news in some ways. This was actually confirmed a few days later when processing of the Comprehensive Test Ban Treaty Organization's infrasound data for the station at Boshoff near Kimberley was actually done. And it showed that there was a massive detonation in the upper atmosphere at about that time. More importantly, it allowed directional data, which showed that it lay approximately north of Boshoff, which was again placing it within Botswana. And the object was probably 1 to 2 meters in size, traveling at 17 kilometers per second, which is meteorite speed, and it detonated at just under 28 kilometers altitude. So we had some information to go on. Now, what I then did was there was a 3-part search to try and refine the data, and I was involved primarily in trying to get eyewitness accounts from people. This mainly involved in this very unpopulated region of trying to phone game lodges to find out if people saw things. And thankfully, a bunch of people did. The first reports indicated that the thing fell to the east of Ganzi, which is somewhere around here. And then we had sightings from the south, but also sightings from the north, which actually had an indication that there was a delayed sound, like rolling thunder, up to 5 minutes after the event. And the key one was the Talpan camp, which is the most remote camp in the reserve. And in that case, the eyewitness reports indicated very startling noise and very bright lights to the effect that people ducked under tables. So it placed us probably in this vicinity. And in fact, that little ellipse there you will see was actually the final ellipse that led to where the search party went based on the other methods. Now, those methods involved using other CCTV cameras to triangulate the position. And we did not know at the time that Peter Jenniskens from the SETI Institute in California had already arrived in Botswana and was working with Oliver Moses from the Okavango Research Institute at Maun to collect this information, which is much more reliable than the eyewitness reports. And again, the triangulation was putting them in a very small area in the reserve. And the final bit of information then came from the collected astronomical data. And this was from what had been spotted on the telescopes and then tracking it through the atmosphere. And what this indicated, the blue line indicates the trajectory with a descent from east to west at kilometer spacing. The detonation altitude where it exploded was at about 28 kilometers altitude, and this is the error ellipse on that. And then we had the evidence from the videos, which is obviously measuring a bright light that is a bit fuzzy, and this was a slightly wider ellipse that coincided there. In addition to that, they then started to play around with the wind data from between 28 kilometers altitude in the ground to work out where the small particles would land. And the ultimate projection after many iterations, not immediate, was that this was the line, the black line, was where the fragments, certainly the finer fragments, would have fallen. So we had all this data converging. It took quite a while to get permits because it was in the game reserve, and I said that was good and bad. It was bad for a variety of reasons. One is that everything had to be done under armed guard because it's a Big Five reserve. And the team that went out, I think, was losing 2 to 3 tires per day because of the ruggedness of the terrain. However, it was good news because when they arrived on the 18th of June, they found out that an international meteorite hunter had already been in the area, had flown into Botswana using the free access data and had gone into the reserve to try and pick up the meteorites and smuggle them out, and had turned away when encountering actually how remote and how dangerous the area was. So it was fortunate that that did not happen. Bizarrely and ironically, the first find after 5 days of fruitless searching was made on the last day when the team left the reserve, and it was made just outside the camp when Sechiro Lesedi went out and spotted this. So that was the first and only meteorite found on the first of the searches. And on the 4th search, these meteorites were actually found in October. So this is the latest find, which is basically half the mass of the total find so far. Now, from the immediately, the first piece was brought back into Maun. Thomas Kohut, who had flown out from Finland, actually did some magnetic density and susceptibility testing. And what he showed was that the meteorite was not the normal chondritic meteorites, but it was actually part of an achondrite group sitting down here, which was very interesting. And the microtomography that was done when it was taken to Finland showed that it was a breccia. So we were concluding that the preliminary analysis was it was an achondrite breccia, which is good because these are quite rare features. So very briefly, what are we talking about with regard to meteorites? Most meteorites are chondrites. These are the ones that we pay most attention to, but about 8% are achondrites. And they look pretty boring because they're actually stony meteorites, but they probably have the longest information history of the early solar system processes. So most meteorites form very close to the origin of the solar system, and they mostly lie in the asteroid belt. And what we see is that chondritic meteorites are really undifferentiated agglomerations of small particles from the initial solar system formation, whereas the achondrites are from larger bodies that were able to heat up and melt completely and then differentiate with the iron segregating to the core and more silicate material towards the margins. So they indicate larger bodies that have been undergone differentiation. And then parts have been liberated either by Jupiter's gravitational pull or by meteorite impacts. So quite a story that can be told from that. So In terms of the achondrites, the rocks themselves are essentially igneous rocks forming from this magma ocean that then differentiates, and they will be from the mantle or crust of one of these planetesimals. But we said that the tomography indicated a breccia, and so what we need to look at is what processes on a planetesimal could create brecciation, and that would be essentially impact. So this thing must have been reworked by impact as part of its history before becoming part of the asteroid that collided with Earth. So just very briefly, 2/3 of all achondrites are what we call HED meteorites. The HED stands for howardite, eucrite, diogenite. And what we know is that the diogenites are essentially orthopyroxene-bearing rocks, relatively coarse-grained, indicating subsurface crystallization. The eucrites are more like basalts or gabbros, so they sit with intermediate compositions, plage and pyroxene in roughly equal amounts normally. And the breccias are given the name howardite, and there's various ways you can break this up between components that are basaltic or cumulate basaltic and diogenitic in composition. So our job then was to try and sort out that classification. We were given 5 samples to look at, and these were very small, very fragile pieces of rock, very tiny as you can see, but even from the first inspection, we could see that we would group them into 3 of the samples, looked like they were igneous textured and relatively coarse grained in terms of grain size, whereas the other 2 we could see were clearly breccias. And so our preliminary analysis was crystalline igneous rocks and breccias, i.e. achondrites or achondritic breccias. Now, because of the very small size and the fragility, we decided to use Caiphas Majola's skills in our thin section lab, and we mounted these as resin blocks rather than try to cut thin sections. So Caiphas very carefully managed to get these very delicate samples in to the resin blocks, and that meant we worked mainly in backscattered electron mode and used the new instrument, courtesy of Worsom Instruments, that had just been purchased, the TEMA instrument, which now resides in the school here. And I'd like to acknowledge Caitlin Stewart, who was very instrumental in collecting the data that you'll see in a moment, as well as Alexander Ziegler, who was a great assistance with the mineral compositional data analysis. So this is what the samples look like, the TEMA false color image, which allowed us to classify the phases. And you can essentially see that this sample here, MPO6, consists essentially of pyroxene with plagioclase and a little bit of olivine. And so we put it essentially down in this corner over here, which would mean it is a diogenite, relatively coarse-grained, equilibrated orthopyroxenite. The other 2 samples that were igneous in texture, 09 and number 19, again showed relatively coarse-grained textures, but here we see slightly more plage than pyroxene. And so when we look at it on the plot, we ended slightly off to the side over here, but consistent with what are known as cumulate eucrites. And so hyperbasal or plutonic basaltic rocks that are crystallizing. And then the breccias, of course, had a much more interesting aspect to them. We had to do a lot more study of them and check every part of them. Some of the things that we were able to see, for instance, was that MP18 actually has a breccia in breccia texture, which is quite important. So we see a brecciated clast within the breccia. Some of the lithic clasts actually have melt veins in them. We found a bunch of things like sintering, silica sulfides, and so on. That's part of an ongoing study that we have. And so when we looked at the overall classification using the TEMA images, we can see, again, the sort of purple-blue color is the pyroxenes. The reds and browns are orthopyroxenes. The greens are mostly sort of a clinopyroxene type composition, and including that melt vein that I was speaking about over here. And then combining that, given that we only had 5 of the 23 samples, what we ended up with was classifying this as being a howardite with a 10 to 15% diogenite component. So the orthopyroxenite component. But a whole bunch of other things have come out of the study, like the exsolution lamellae within the pyroxene. So you can see the calcium-rich pyroxene exsolution lamellae as the green stripes only found in the central class, etc., etc. So a lot more history that we can see there. In terms of the mineral chemistry, we were then able to confirm what the TEMA analysis was actually showing us. So of the 3 samples that were igneous textured, we found that the plagioclase compositions were towards some of the most calcic plagioclase compositions seen in diogenites and in cumulate eucrites. And so we believe we were consistent there with what we saw in the rest of the textural analysis. The breccias, however, indicate a wide range that suggests a basaltic eucrite and a diogenite component within them. So we can see these bands over here indicating a wide range of plagioclase compositions. And then if we look at the pyroxenes, it turns out that most of the pyroxene is essentially low calcium pyroxene, but we do see some exsolution. However, it's very fine grained, so we get this smear of data that isn't really real. We're just getting contamination there. But again, most of the pyroxene compositions are indicating a diogenite to cumulate eucrite range, with a little bit overstepping towards the more Faroan basaltic eucrites over there. So just to wrap it up, we see at least 2 breccia events. We're seeing melt breccia veins within both the breccia itself, but also here you can see in this magnesium element map from the TEMA, we can see this zone here with brecciated material in it, a BSE image close up here, showing flow textures. This is a melt vein. What is interesting is that this melt vein seems to be wholly crystalline as a result of Raman analysis. And this will be interesting because it means fairly deep-seated formation and then crystallization. It is not a glass like we see in many meteorites. We are about to cut the blocks and make thin sections so we can look at shock effects in the minerals, as well as some of the other features like the melt veins in more detail and so on. So we're still working on the sequence of events. So what did our petrographic and mineral chemical data contribute towards this large study? It showed that the Motopi meteorite was indeed an HED class A chondrite, and therefore that it comes from a relatively large parent body that was itself then able to differentiate. Cumulatively, putting it all together, there's enough diogenitic component within the sample suite that this would be classified as a howardite breccia. And then the presence of the diogenite implies that at least one of the events, meteorite impact events that created the breccias, must have excavated down fairly deep. So a large differentiated body such as this one, the diogenitic component at level 5 is probably more than 15, 20 kilometers below the surface. That would require a significant impact, possibly in the 100-kilometer or more range. So that's what we have. And we know that at least 2 breccia forming events, possibly more, have happened, which would suggest repeated processing of the sample before it left the parent body and headed up on its trajectory towards Earth. So we have evidence of magmatic differentiation history. There is other evidence that we're working on now on thermal metamorphism. We can see the impact processes. And so what we're concluding is that Motopi Pan, the asteroid 2018 LA, was part of the liberated regolith or surface layer, brecciated and churned up surface layer of a large differentiated asteroid somewhere in the asteroid belt. And I'm going to call it, conclude there, to hand over to Lou, who is then going to talk about some of the other evidence that was brought to the fore from the astronomical studies, from the geochemical and geochronological and isotopic studies, and how we track back now to what the possible source might be. Thank you.
Thanks, Roger. Lou, we're going to hand over to you now. And you'll just need to unmute, Lou.
Okay, I'm muted. I've started my video, and I'm about to share my screen.
Yep, that'll be great, Lou. Thanks.
So is everything cool now, Grant?
Yes, we are seeing your screen. That's fantastic.
Okay, cool.
So you can go for it.
So let me just maximize this. And I want to get rid of this panel up here. I don't know how to do that.
So we don't see your panel, Lou. So
Yeah, I know, but it's in my way, so I want to get rid of it. Okay, I brought it to the bottom. Okay, so thanks, Grant, and thanks, Roger, for your part of the talk. And so now I will take over and say a few words about some things here. One of the unique things about this work is that in a single paper, it contains pretty much everything you would want to know about a meteorite. And so I'm showing here a list of the various assortment of measurements and observations that were made and included in the paper. And I guess this explains why there are 66 authors from 44 different institutions, from 4 different continents. And so when Roger asked me to join him in this talk, I have to confess that I never really read this paper, except for the parts that we were involved in. That's the petrography and mineralogy kind of stuff. And so needless to say, I learned a lot by doing this. So Roger has already spoken about the recovery aspects and about the petrography and mineralogy. And I'll speak about the aspects that are highlighted in red. I won't list them. And I'm going to ignore the ones that are not highlighted, mainly because these are kind of either descriptive or, you know, they speak to mainly the characterization of the stones rather than say a lot about the origin and the history. So let me go to the next picture. So this remarkable set of photographs, which were taken by a telescope somewhere in Arizona as part of the Sky Mapper program, which part of what they do, as Roger said, is to try to detect Earth crossing objects. So that means pieces of asteroids or maybe comets or maybe some space junk, and they want to know if any of these moving objects might have Earth crossing orbits. And so what you see here in this picture is a series of photographs taken about 15 minutes apart, about 8 hours before the impact actually occurred on the 2nd of June, 2018. And so the Sky Mapper survey actually said, well, yes, it does look like this is going to be an Earth crossing object. And they estimated that it would crash into the Earth somewhere between Australia and Madagascar with 85% probability. It actually went a little bit further than that and landed in the Kalahari of Botswana. To me, the most amazing thing about this set of pictures is that they found this thing at all in the first place, considering that this object is about 500,000 kilometers away, and it is only about 1.5 meters across. So this is a tiny object that they were able to track. So Roger has shown you some of this evidence already, the movies, so ground-based videos of all kinds of different types of the fireball. And they actually were able to use shadows of the fireball as they moved across a parking lot or a doorway or something from all kinds of different directions. So here is the landing site. And so all these different videos at different angles, combined with the astronomy, the telescope observations, actually allowed a very precise orbit for this object to be constrained. And turns out that that the orbit that was calculated is very similar to another meteorite from Turkey that landed about 10 years ago. It's called the Sarishishek meteorite. And by amazing coincidence, it's exactly the same type of howardite that what we have described in Roger's description a little while ago. So here you have, in fact, the only 2 meteorites recovered that were tracked in space. And they both happen to be the same type of meteorite. And I think that's a startling coincidence. So based on all of these astronomical observations, video observations, and so on, the orbit that was calculated for what we now call the Motopi Pan specimens is actually about 750 times more precise than the orbit derived from the Turkish meteorite. And that orbit takes it back to a part of the asteroid belt, a part of the inner asteroid belt, where one of the largest asteroids called Vesta is located. And so that's where we think it comes from. I'm trying to forward here. I'm in trouble, Grant, because I can't advance my slides.
Lou, I think you've gone into pen mode. So if you just press escape on your keyboard, you should go back to your mouse and then you should be able to.
No, it's not working, Grant.
So if you click on there's really some little dots on the bottom left of your screen.
Oh, yeah. More.
Just go back to your laser pointer and you should be able to change slides.
Back to my laser pointer. No, that's pen mode. So how do I get out of this pen mode?
At the bottom bottom left of your screen, Lou, there's a bunch of options that will
Here we
bigger.
go.
There we go.
Okay. All right. So this is my next slide. I don't know how to get rid of this drawing that I made on there. So this is a little animation of the orbit of this meteorite, which was at that time called 2018 LA. That's the orbit shown in pink here, with respect to some of the other planets. So the Earth is in blue, and here in light blue is Venus, and in green is Mars. And what you can see here, so this animation is over a 2-year period, and it shows you the trajectory of this object in space as it eventually landed on the Earth. So what I'm asking you to do is watch the pink orbit. That's the achondrite that is going to eventually land on the Earth. And at this point, when it approaches the Earth, this is bang, 2018, June the 2nd at about 5 p.m. in the afternoon. So you can use these. This is a very schematic thing. It's not to scale at all. And you can watch, if you want, the speed of the asteroid, the distance from Earth, and so on. And it's instructive about how meteorite orbits intersect Earth-crossing ones. Okay, so I said that the well-constrained orbit takes it back to a part of the asteroid, the inner asteroid belt, where the asteroid Vesta is located. And here in this picture, I'm showing you the four biggest asteroids in the asteroid belt. So that is Ceres, 946 kilometers in diameter, Vesta, 525 kilometers, Pallas, 512, and this one I can't see because there's something in the way, but it's 430 kilometers. So the one of interest is Vesta here. And it's interesting, maybe you may not be aware that asteroids are numbered in order of the time at which they were discovered. And so it turns out that Vesta, which is the second largest asteroid, was actually the 4th one to be discovered. So Ceres, Pallas, and this other one were discovered before Vesta. And the reason for that is because of the composition. So the other 3 asteroids are very light colored. They have a high albedo. And the reason for that is because they are made out of carbonaceous chondrite stuff or chondrite meteorite stuff. But Vesta is much darker in color with a low albedo, made it hard for it to be discovered. And in 1804, I think it was, Vesta was discovered, its orbit calculated by some guy in Germany, I think it is. So here's a better picture of of what Vesta looks like. This imaged by a NASA mission called Dawn, which sent a spacecraft to Vesta to photograph it and take all kinds of data. And I think after Vesta, it moved on to Ceres, the largest asteroid. But here's what Vesta looks like up close. To me, it looks like a potato that's covered with impact craters. And so, so here's an image from 2011 when the Dawn spacecraft imaged Vesta. Okay, so let me talk a little bit about some of the data that were collected. And one of the important things that we would like to do when we have a meteorite, we're trying to figure out where it came from, is to measure its reflectance spectra. So basically what you do is you shine a light, some kind of special light at a meteorite, and you measure the reflectance as a function of wavelength using some kind of a spectrometer. And what we find is that all different types of meteorites have different reflectance spectra. So for example, here's what this blue line is what a ordinary chondrite looks like. And you can make a resemblance of that spectrum to a certain type of asteroids called S-type asteroids, exemplified by this asteroid 7 Iris. But more importantly for us is that the reflectance spectrum of Vesta is very similar to eucrite meteorites, or in general the Hed meteorites, of which the Motopi pan specimens are examples. So what's important for these Hed meteorites is that there are two absorption bands, one at about 0.9 microns, another one at about 2 microns. And I can show you the results for the Motopi pan specimens. So, so here what you see is the absorption band at about 0.9, and then this more confusing looking one at about 2. And what controls this is the mineralogy of the specimen. So there's a bit of a shift here in the 2 micron absorption band, depending on the exact mineralogical nature. So it turns out that the diogenites, which are shown in red, have a bit of a lower wavelength for its absorption spectrum. And so that's the diogenites. They're orthopyroxenites. But if you add plagioclase, you shift the position of this absorption band to the right at higher wavelength, and the Howardites plot in between the two. So this is one thing you can do. You have a bunch of meteorites, and you can compare them to the known reflectance spectra of planetary objects, like planetary surfaces, satellites like the moon, or asteroids. And you can do this with telescopes or with spacecraft. And so that's a pretty interesting thing to do. And it supports the idea that these things come from Vesta. Another thing that's important to do is oxygen isotopes. And what's important here is that these are not normal oxygen isotope measurements that we're all familiar with, which rely on oxygen 16 and oxygen 18. But in the cases here, we're studying actually the additional abundance of the isotope oxygen 17, which is a very, very small abundance isotope. And there's only a few labs in the world that can do this, just a handful of laboratories in which we can reliably make these kinds of measurements. And what you see is that the position on this diagram, which is called the 3 isotope plot, because it uses 16, 17, and 18, you can use it to define various parts in the solar system where meteorites and other stuff may have been derived from. So for example, this black line is the Earth line. It's called the terrestrial fractionation line. It's a mass fractionation line, and anything from the Earth will plot along that line. So that includes rock, soil, air, water, plants, a piece of pizza, anything you can imagine will plot along that line. And these measurements are made so precisely. I want to say that they're smaller, the error bars are smaller than the thickness of the line, but that's probably not quite true, but maybe close. So what you see here is that there's the Earth line, and these green symbols are the Martian meteorites. So we can define a separate fractionation line from Mars, and then there is another fractionation line for the Hed meteorites, which we think come from Vesta. So, so different parts of the solar system where these objects were formed initially have different isotopic compositions depending on their distance from the sun and things like that. What's interesting here, just as an aside, is that everything from the moon plots on the Earth line, very close to the Earth line. And what that says is that the moon formed in a part of the solar system that was very close to Earth. So the theories that talk about the origin of the moon have to take that into account. So it does not look like the moon was captured by the Earth and have it initially form at some other place in the solar system. Okay, so here are the 3 isotope results for the Motopi pan. And once again, they plot with the other Vestoid objects, the other Hed meteorites. But you see a bit of a scatter here. These are very precise measurements, but there is a bit of a scatter here that is different from a very linear straight line. And so what this says probably is that there's another component mixed in with these specimens. So in this picture, the circles are the Motopi pan, the X's are the Sarışişek from Turkey, and here we have this mass fractionation line that has a bit of dispersion caused by some other component. And we think we know what that component is. It's probably a piece of chondrite because here are all different variations of fields for different types of chondrite meteorites. And there's a large assortment of areas in this diagram where CM chondrites as opposed to CV chondrites as opposed to the ordinary chondrites plot. And so based on the oxygen isotopes, we think we can say that there is a CR component, a chondrite, a primitive chondrite component that was mixed in somehow with the Motopi pan specimens on the surface of Vesta. So it's probably a sprinkling of chondritic material that was scattered on the surface of Vesta, probably by older impacts. And we can see that again here in the chromium isotopes. So chromium 54 is an isotopic measurement that is commonly made for meteorites and for impact structures as well, because on this basis, you can begin to distinguish the different types of chondrites. And so what we see here for the Motopi pan measurements, and there's 3 of them, red, black, and blue. And so you can plot a mixing line between average eucrite and different types of chondrite meteorites. And most of our specimens from Botswana plot in this region with only a very small component of chondrite. But this one specimen, MP17, it looks like it has about 10% of a chondritic component. So that's interesting because it says something about what's going on the surface of the parent body, presumably Vesta. So the panel on the right is a diagram of iridium versus neon 20 isotope, but I would prefer to talk about the neon isotopes in the next picture. So what is very commonly done in meteorite studies is to study the cosmogenic nuclides, which are isotopes that were created when high energy cosmic rays interact with the nuclei inside the specimens, inside the solid specimens. So in terms of cosmic rays, these are very, very high energy particles traveling probably close to the speed of light. And there's two types of those. There are solar cosmic rays and galactic cosmic rays. These differ in terms of their isotopic compositions of neon. The solar cosmic rays are pretty much minuscule. They're peanuts compared to the galactic cosmic rays, which are probably caused by supernovas over the course of galaxy history. And they're shooting these particles all over the solar system where they can interact with things like asteroids and meteorites and whatever. So all of these isotopes are cosmogenic nuclides, but I don't want to talk about all of them. I'll just mention the three ones that are, I think, more important: helium-3, neon-21, and argon-38. So here what you see on these pictures is the neon isotopes, which can be used in a diagram like this to tell you something about whether or how much solar versus galactic cosmic rays you're talking about. In our case, all of the specimens plot in a very narrow box indicating almost zero percentage of solar cosmic rays. So it's all galactic cosmic rays. And then there are various other places in these pictures that you can use to talk about other components. And so these stars on the left side of the left picture here, various things: solar wind, which is something different from solar cosmic rays. Solar wind plots there, and then there's various components here. The important ones are terrestrial air, atmosphere, plots about here. And what we can see when we zoom in on this result for the meteorite specimens from Botswana that were measured is that almost all of them plot in this region here. They're all uniform. One of them has a little bit higher neon-21, that's NP06. And the reason for this is because this one is a diogenite. And so it depends on the chemical composition of the target material as to how much of what particular cosmogenic nuclides are produced. So that we can explain by its being very pyroxene rich. This one up here is a little different, and you can draw a line between what you expect for galactic cosmic ray exposure is a mixing line between that and probably air. So this meteorite here, this specimen, contains a very small amount of probably terrestrial atmosphere, terrestrial air, that could have been implanted into the thing after it landed in Botswana. So what you can do is remove that component, and if you do that, it would plot down here with the other eucrites. Okay, so in terms of cosmogenic nuclides, what's more important, I think, is the fact that by using them, you can determine a cosmic ray exposure age, which represents the time since a meteorite was ejected from its parent body and its arrival on Earth. So basically, the time it spent in space since when it was impacted off the surface of its parent body and then landed on the Earth. And the way this is done is if you know the density, and if you know the size, and if you know the chemical composition, you can use the measurements of helium-3, neon-21, argon-38 to calculate a production rate, which are these numbers here in P. They don't have very much meaning. But if you know the half-life of these different isotope systems, then you can compute what we call a cosmic ray exposure age. And so here are the results for helium, neon, and argon. And you'll notice that, so we're talking about something in the range of 11, 12 to over 20 million years. So that's going to represent the age of the impact event and the age of the crater on the parent body, presumably Vesta. So what you'll see here is that the the ages for helium are a little bit lower than for neon and argon. The reason for that is that helium has a very high diffusivity. And in 20 million years or so, a little bit of it has diffused out of the minerals and the components of the meteorites. And so you really don't want to consider the helium cosmic ray exposure ages. Better are the neon and argon ones. And the guys who did this work figured out an average, a best guess or a best average of the cosmic ray exposure ages for the Motopi pan specimens, 19.2 plus or minus 2.4 million years. That's the age of the impact event and the time that the meteorite spent in space before landing on Earth. So now we can have a little bit of fun because we can start now to relate this to what we know about the surface of Vesta. So this diagram shows the craters, all the different craters on Vesta. So on the x-axis, the crater diameter in kilometers, and the y-axis is the crater formation age. And the crater formation age is determined by this kind of a black magic method that a lot of planetary scientists who study the surfaces of planets and asteroids, they can determine the ages of different terrains on different parts of planetary bodies. And so what they do is they do a thing called crater counting. And by knowing the approximate crater frequency, the crater flux or the impact flux rate, they can compute different ages for different terrains on different parts of planetary bodies. And so these are the results for Vesta. And what you see here is on this picture where we have the cosmic ray exposure age on the y-axis and the three different isotopes that were used, you see that the neon and argon collectively give a result of about 19.2 million. Let's ignore the helium because of diffusion. And so that is thought to be the age of the crater on Vesta that gave rise to the Motopi pan specimens. This Turkish one, Sarışışık, has a little bit older cosmic ray exposure age. And so we can begin to think about linking these to specific craters on the surface of Vesta. So here's a picture of, I guess it's the southern hemisphere of Vesta, showing all the different craters. And so let's begin to look at this a little bit. There are two big craters. These are massive impact basins, probably very old, that are hundreds of kilometers in diameter. And then there's a whole bunch of smaller craters. And based on the cosmic ray exposure age and the crater counting statistics, the guys in our present paper are proposing that the Motopi pan meteorites came from this crater called Rubria, which is, I don't know, what is it, about 10 kilometers in diameter? I can't see this part of my slide. Whereas this other crater, Antonia, is the one that gave rise to the Sarışışık Turkish meteorites because of the ages. But, you know, if you ask me, all of these ages are within error of each other. And so it's very hard on the basis of these kinds of age determinations to specify exactly where the crater source is on the surface of Vesta for any of these. But they went a little bit further and they said that because the Motopi pan meteorites have very little solar wind component, whereas the Turkish meteorite has a much higher component of solar wind. And solar wind is something that accumulates on the surface of planets and asteroids. And so you'll see that the Antonia crater is located in the middle, or very close to the middle, of this big impact basin called Venenea, whereas the Rubria crater is located on the edge. And so the inference is that a crater near the middle is going to be something that contains more regolith and a higher proportion, perhaps, of a solar wind component. The Rubria crater on the edge is sitting at a topographic high, and it might be expected then to contain a lower amount of solar wind component. Okay, finally, we'll talk about the uranium-lead isotope stuff. One of the team members actually found some zircons in, I don't know how many specimens, maybe just one of them, and also some phosphates, apatite in particular. And they were able to find enough zircons and enough big zircons so that they could try to measure the age. And that's exactly what they did in situ. So they used a thin section of one of these things, found the zircon, and put it into a SIMS instrument. So basically an ion probe. The one they used was the instrument in Beijing, but it's basically identical to the one that is used by our friend Michael Wiedenbeck in Potsdam in Germany. So anyway, the results here are very interesting. So the zircons produce an age of about 4.56 billion, and that is basically the age of the solar system. So this is going to record the time of probably crystallization from the magma ocean that happened just after accretion of the parent body Vesta, and so that's basically dating the beginning of the solar system. The phosphates, the apatites, give a much younger age, 4.23 billion, and the interpretation here is that this is a resetting event. It reset the apatites, which are not as robust as zircons, but the zircons were not affected. So this is a resetting event, and it may in fact date the formation of that big Venenaya basin that contains the Rubria crater that at 20 million years ago gave rise to the Motopi pan meteorites that we see today. Okay, so this is the end here. Just a little summary. So the types of data and the inferences, we have a very nice orbit, 750 times more precise than the Turkish one, based on telescopes and video cameras. The orbit takes it to a part of the solar system where Vesta is located. So we can use the impact energy and the cosmogenic isotopes to constrain something about the size of the object that crashed into Earth, only about 1.5 meters. The mass was about 5,700 kilograms. And as Roger so expertly pointed out, based on the petrography and mineralogy, this is an Hed meteorite, probably a howardite, polymicted breccia. The reflectance spectra links it to other Hed meteorites and Vesta. The oxygen and chromium isotopes demand that there has to be a bit of carbonaceous chondrite component on the surface of Vesta that got admixed into there somehow or other. And the cosmic ray exposure age probably dates the ejection event that sent this meteorite shooting off Vesta and eventually landing on the Earth a couple of years ago. The lead isotopes, uranium lead, tells us something about the formation of the earliest crust and dates the time of solar system formation. The phosphates date resetting during probably this very large Venenaya impact basin event. Okay, so that's it, Grant. You can take over.
Thank you so much, Lou. That is fantastic and really, really interesting. Thank you both, Roger and Lou, for that. Just to remind everyone, you can ask questions any way you like, either by typing into the Q&A chat or just typing into the chat box, or you can raise your hand and we'll allow you to speak. So I can see there are already 2 questions in the Q&A chat. Well, actually, there's one serious question, and I'll ask Roger to answer this question. From Charles Day, who says, any idea how much the original meteor or bolide weighed?
So am I live?
You are.
Hi, Charles. Yeah, I think Lou's final screen probably answers that as well. So somewhere in the region of 5 to 6 tons, I guess. But I mean, the idea was that this thing is probably the size of your engine block and bonnet of a medium-sized family car. So 1.5 meters across. There's all sorts of data that was collected from the astronomical observations. That Lou spoke about how the heck do they spot these things in space, given that they are dark. We only see it when a side is reflecting on the sun. And so the initial, the paper indicates that the object was not totally round, it was faceted and slightly distorted, and it was spinning as it came in. So yeah, you know, the thing that fascinates us is 6 tons of material comes in. How much actually reached the ground? We've collected 215 grams. And it's, I mean, I would argue we probably spent close to 100,000 Rand actually on expeditions to find it, to find that. There could be bigger pieces downrange, but it's more difficult to try and find those big pieces because you might get 1 or 2 of those, whereas you might find lots, as we have, of the small sort of 10, 20, 30 gram pieces, which lie in a particular position. So probably a lot burnt off, but possibly maybe a few extra kilograms or so lying out there in the lion and elephant infested Central Kalahari Reserve. Lou, I don't know if you have anything to add to that.
No, that's great. Yeah, the estimate based on the impact energy and the kinetic energy and the astronomical stuff is 5,700 kilograms, so 5.7 tons.
Okay, I'm going to. Sharad has a question.
No, he does, not a comment. Okay, Sharad, Grant has to go to his computer to get you to talk. And yes, indeed, Chris, congratulations to Caiaphas. We looked at these things when they came to us, and they were wrapped in aluminium foil and FedEx to us and monitored every step of the way. When they came, I mean, you did not want to, we should have been wearing masks because you did not want to sneeze, because half your sample would have disappeared into the room somewhere. And yeah, Caiaphas did an amazing job, particularly as you can see how friable some of them were in getting them ready for us. He's now going to take the big step and actually try and cut the resin block and polish it down so we can do some transmitted light microscopy, which will probably give us all, well, him at least, gray hairs, because the other two of us have already got the gray hairs.
My hair is pink, not gray.
All right, Sharad, you can go for it and ask your question.
Okay, I've got a couple of questions for Lou. Great talk. Lou, at the beginning of your talk, you mentioned that this Motopi Pan meteorite is just one of 2, together with the Sarishik meteorite in Turkey, for which there was an orbit calculated, and that was, you know, the precise landing spot was calculated. But you forgot about the very first one, which was also described by the first author of your paper, the Yeniskins, which is the Almahata Sita meteorite, which was the very first asteroid which was spotted before it crashed on Earth to produce a meteorite that landed in Sudan. So that was actually, there are 3 meteorites for which we have had orbits calculated before they crashed.
Yeah,
now,
these are yeah, you're right. There is a 3rd one. Actually, there's a 4th one. So these are all meteorites that were recovered after observing their trajectory in space by telescopes. The 4th one actually was never recovered because it crashed into the Atlantic Ocean and sank, so we never got that one.
Okay, so I have another question concerning the oxygen and chrome isotopes, which gave you a chondritic component as well. And you interpreted that as suggesting that there were sort of chondritic meteorites lying around on the surface of Vesta, so that when you know, this meteorite was ejected, there were pieces of this older component lying around that got incorporated. But what about the actual object that crashed onto Vesta to produce that crater and to eject the material that forms the meteorite, the Motopi pan. Isn't it that meteorite a possible source for this chondritic component?
It could be that, but then when you look, it makes a lot of sense for the chondrite to be responsible, because chondrite is the most abundant type of asteroid, the most abundant type of object that creates meteorite craters, and Vesta would have been subjected to that. But if it was actually a component in the bolide that ejected Motopi pan from Rubria, then you have to find a way to get it inside of the eucrites and the howardites and the diogenites, which is possible. But I think it's more likely that it's kind of a sprinkling of chondritic material that just exists on the surface of Vesta from billions of years of previous impact results. So I wanted to, I forgot one of the things I forgot to mention was at the chromium isotopes in particular, to a lesser degree, the oxygen, are used in terrestrial impact studies, such as Fridafort or Sudbury or any of the other ones, where if you can identify an impact melt or something like that, then you can use that impact melt to try to characterize the nature of the bolide. So in Fridafort, for example, I think they have determined, Roger, you correct me if I'm wrong, it's some kind of a chondrite, an R chondrite, is it? And then for Sudbury, it's also a chondrite, but a different kind, a carbonaceous chondrite, I think it is. And so the chromium isotopes are very good in distinguishing different types of meteorites and their interactions with surfaces and stuff like that. Does that help you, Sharad?
Yeah, but you've brought up another can of worms. If you suggesting that there's a sprinkling of different chondrites over a long period of time on the surface of Vesta, then they should have differences in composition in the chrome isotopes. Do you see that in the signal from the Motopi pan meteorites?
Well, we only measured, they were only able to measure 3 specimens.
Okay.
And 2 of them show not a very big component of a chondritic sprinkling. There's one of them that contains 8 or 10%. And what this probably says is that the Motopi pan specimens were derived because there's such a small amount of chondritic material in there, that it was probably derived from somewhat deep in the surface of Vesta. So I don't know what that means, maybe a few tens of centimeters, so that the specimens were protected, shielded from the sprinkling of chondritic material. Need a whole lot more analyses of these chrome isotopes in different specimens to get a handle on what the spectrum of chondritic material sprinkling on the surface of Vesta is going to look like.
Great, thanks.
Thank you, Sharad, and thank you, Lou, for that comprehensive answer. I think that Anthony Rutherford has a question as well. Anthony, you can just unmute yourself now and ask. Anthony, you just need to unmute.
No, Grant, I accidentally pushed the wrong button. Sorry, thanks.
No problem. Thank you for joining us. Great having you in the audience. The last question, which is an easy question, and I'll give this to Roger, is from George Henry. And he asks, where is the paper published? Because I guess he would love to read it.
Yeah, that was a story in itself, because the initial hope was to get something out in Nature or Science, and it was very touch and go for several months. But eventually, given the size, because it's the equivalent of at least 3 papers in total length, it's 50 pages. It's come out in Meteoritics and Planetary Science, MAPS, as we call it. So that's the main journal of the Meteoritical Society.
Okay, fantastic. I don't see any other questions coming up. I'm not sure if there's any questions from the audience that's live in with Roger there. Roger, do you see any hands in the audience?
So I mean, just to say then, just to add to what Lou answered to Sharon, I think if you look at some of the recent very high resolution images from some of these recent space missions to the asteroids, so Hayabusa 2, I think, they actually got very excited in finding foreign fragments lying on the surface of those asteroids, suggesting that there were low velocity impacts into these asteroids, and so you're likely to get a contaminated surface layer associated with these with asteroids that are out there for a long time. So not everything is high velocity impact. So we see that. And Lou, the Fredefort thing, chromium isotopes didn't really show anything. The meteoritic component in Fredefort was proven by rhenium-osmium isotopes, but I think they've just shown for Chicxulub, the dinosaur killer, also that it was probably a carbonaceous chondrite that was the cause of the Chicxulub crater as well. So Sudbury and Chicxulub, the two of the other big three, are carbonaceous chondrites.
Thank you.
Okay, well, thank you both, Lou and Roger, for that really fascinating talk. Fantastic to hear about that extraterrestrial object now on Earth. And it's left for me to just advertise a few more talks. So let me just get my screen sharing here. And so you'll see that tomorrow we have a special talk at lunchtime, which is from Andrea Giuliani, who is visiting us, one of the first visitors we've actually had live in the department for almost 2 years. He's from ETH in Zurich, and he'll be talking about an early Phanerozoic shift in surface and deep Earth carbon cycles, which should be really fascinating. So you're welcome to join us both here in the School of Geosciences or online, and there'll be a notification coming out tomorrow for that talk. And then next week, Judith Kinnaird will be talking to us about the importance of critical metals. And that advert will come out early next week. So thank you all for joining us, and thanks once again to Lou and Roger for a really great talk.